All right. So I can sort of continue where Jim left off. I'm working with Jim, looking at the performance of what you just heard, the processing. So you heard his talk. I'm going to talk a little about the software we developed to evaluate the performance, to monitor things, and give some example results and talk some speculation on where we might go. So the software that I've been working on is put in this package here, so you can go take a look at it if you want to in GitHub. It does a number of things. One is Parsl provides a monitoring database, and that monitoring database monitors what each process, what each task does. And so we look at that database, and one of the things we do is to sum the contributions from all the different processes and see what the totals are, which is not as easy as it sounds because the samplings are not synchronized. And then another thing that we sort of put on top of that is to measure the latency. When does one task end and the next one stop? How long does the system take to get the next job going? And we just do this by making chains of tasks. We don't actually have a strict mapping, knowing where one ends, one starts. Another thing to do is we use PerStat to write to our log file, so we can pull out, in addition to this sort of information, we can get the CPU speed and instructions per cycle. And then we added system monitoring. This is process level monitoring. We do system monitoring, what the CPU utilization is, what the memory use is, the IO, et cetera, across the system. For us, the system is 128 physical CPUs. And then there's a test. We have a test program just called Parsl test that it's a CPU intensive things. It runs for a fixed number of instructions. We specify the time, but that's calibrated, and so we can run jobs and see how it performs under different loads. When multiple tasks are run, we vary this time over a factor of 2, so the tasks don't get stuck into phase, which is a separate issue to study. And then we have notebooks to generate performance plots based on our analysis of these all these monitoring systems. So I'm going to show you just a few examples of those monitoring plots. For the plots that I'm showing you today, we're running this Parsl test task with an average running at 20 seconds per task. So it's a pretty short jobs, but a lot of the DESC single frame tasks that you just saw from Jim run in about that amount of time on this machine, Perlmutter. This machine gives us, when we use this machine, we get exclusive use of 128 physical cores as corresponding to 56 virtual cores. So we want to take advantage of all that. Most of the Python code that I'm going to use for this stuff is almost all in Python, and the code is installed on CVMFS. That's important, because we'll see when we use different file systems, we get different performance. And as for these tests, this work queue executor has been tuned, or parameters have been chosen, so that if we're running it, if we're keeping up, it'd run 100 tests. We'd be running 100 tests per node. And so each page is going to show you 2 plots. The first one is running on 1 node, and the second one is running on 16 nodes. So it's running 16 times as many tasks. So it should finish it. Should finish at the same time if things scale. And so the first plot is our sort of most important plot, is the throughput plot. This shows the blue curve is the integrated launched jobs. So we see up to 5,000 jobs is what we want to do. And then the orange and green curves are the jobs that have started running and finished running. And so when the green one reaches 5,000, we're done. And then here, this took 19 minutes to run 5,000 jobs here. When you run on 16 nodes, that is the same load on each of the nodes, you can see it takes longer, and the reason is that we can't launch jobs fast enough to keep up with this, to maintain the rate at which we process them. And so it runs a little bit slower. Another view here, this is just showing the number of processes that are running at any given time in purple, and the green curve is weighted by CPU utilization. So that this one looks pretty good. We're running we're getting utilization about 90%, which is about right. We're also only running about 90% of our goal processes, and that's because we can't quite keep up with Parsl can't quite keep up with what we asked it to do. With 16, but it's not so bad. But when we go to 16 nodes, then of course we have this problem we saw on the previous page. We're not getting up we're not getting close, especially once we get going. We're only running at about 60% of the level we should be running at. And the last plot is a latency plot. And it's going to show the same things. Again, this the blue points are the runtime. So this is there's one entry for each task here, and this is a function of task start time. And so you can see our jobs are running at about 20 seconds, and then we have about 2 seconds of latency. That's one job finishes, and the next job starts 2 seconds later. And so that explains why we're getting 90% of our jobs, because it's taking 10% of the time to start the next job. And then again, of course, because of what you saw on the previous page, this latency has to go up when we're running it on the 16 nodes. So I want to sort of start with the positive view. Parsl has really been a success for DESC. We've been able to, and it's enabled processing of image workflows at NERSC and other sites. Today, we've been looking at simulated data because that's mostly what we have. And we're using mostly this machine, which is about to be decommissioned, the Corey Haswell, at NERSC. We're going to scale up, though, in coming years. We're going to be looking at larger data sets with real data. And we're going to be switching to Perlmutter, which is faster, has more CPUs per node, and we'll be using more nodes. So we've been carrying out studies to identify what issues might arise when we do this. So we added the monitoring to try to find when we have bottlenecks, to see where we have problems, and then what's causing the problems. And some issues have been identified, and those are listed on the next page. So the first is that intrinsic latency we just saw a couple slides ago, that it takes about 2 seconds for a work queue to get the next job started. And then we think that this is due to when it builds its jobs, it has to do a lot of Python imports. And because the code is sitting on CVMFS, which is a little bit slow, that's where we think that time is coming from. So we can make this number better, and we can make it much worse if we change to a different file system. Scaling, though, is a more concerning issue. We really couldn't get the launch rate we needed. We can only get a launch rate of about 1,000 to run about 1,000 concurrent processes, and that's the best you can do with this particular executor running from a single Parsl host. But this is we can get twice as much if we use the high throughput executor, but then we don't get that nice balancing of resources that we talked about earlier. And in any case, our production goals are probably going to require us to go significantly above that. I didn't show you, we see stalls sometimes. We see periods where suddenly things stop running for tens of seconds, or very few tasks are running. We don't understand where that's coming from. We suspect it's a NERSC file system issue, but I just mentioned that. It could be a Parsl issue. Task synchronization, again, I didn't show this, but if when we start all of our tasks together and they run for about the same amount of time and the memory grows for all the tasks, then what happens is the memory grows with time, and then it drops off when the job is finished, and it grows and drops off again. And so where we're memory limited, which is often the case, we're limited by the peak when all the jobs are coherent, which would be much higher than the average memory if we could spread them out. And we can probably get around this just by not starting the jobs all at once, but of course, then that costs us a little bit of resources up front. And so we probably want to run longer, since we want to run longer things, run longer batch reservations and not just do one set of processes. The task variation, Jim already talked about this. We have a wide range of tasks, runtimes, and memory usage and stuff, so we need to balance those things in some way. And although I guess we've been focusing on balancing processors and memory, but there's also I/O happens at the end of the job, and maybe database access at the beginning when we want to build our DAGs. So we might want to take those resources into account as well. And this DAG creation can be quite slow, which again, I suspect is a database issue. So how do we address these issues? So this proposed production model is, I think, a single Parsl instance is not going to be sufficient. So we need to tailor the solution to match our problem. And as Jim already described, this is our focal plane and our sky map. Jim already talked about all these things. But I mean, here's a cartoon showing what our production DAG looks like. There's actually more steps in each of these pieces, but we do the single frames up here, and then we do the patches down here, and each patch depends on many frames. But if we break this, if we say we're going to run the red stuff first, or some known part of the red part first, then we just have a bunch of little DAGs instead of one giant DAG. And so it becomes a significantly different problem. So we split the production into those two stages, the single frame and the patch processing. I think the way to address scaling is to have a more hierarchical production system, or at least have a distributed one. You don't want to have one job production manager. You want to have many job production managers. And then you want to have some top level thing looking at those and somehow passing jobs to them. And so that's those production managers, the top and the job have different requirements. Both or either or neither of those could be Parsl or Parsl based. The job production manager, that's maybe certainly naturally a Parsl sort of thing. Some things would be nice to add is if the production manager in fact could produce its own DAG, because that takes some time in itself, and then consume that and use that to specify the rest of the job.
1 minute, David.
Yes, sorry.
About 1 minute.
Yeah. So what we're saying here, and we're saying for other purposes, it'd be nice if this production manager was a dynamic thing. By that I mean we have specified initially we have a DAG or a few of these sub DAGs. It would be nice if we could add more of those as time progresses and continue to fill in the resources. And then of course we'd like to do that in some sort of mode where we communicate with the top structure. I see I'm out of time here too. So we plan to continue these studies and demonstrate that we can operate at scale, as I claimed here, and demonstrate that doing this distribution will allow us to address those issues. Thank you.
Thank you. Any questions? I had one about latency, but I think you went and well answered it. So good job there.
I think Ben Tovar might have opinions here, but the first point of performance reusing the Python environment, I know there's some work in WorkQ to do that. The way that HText works in Parsl is that it can reuse the Python state. And I think Ben wrote our paper on lightweight containers, talked about some of that, didn't it? Ben Tovar, you're still there?
Yes, that's correct. And we're also working on having the worker have the Python environment already there, so you don't have to do the imports. But that's totally work in progress. But yeah, this kind of latencies are in our minds.
Yeah, I think we could probably get around that one. In terms of the throughput, based on some testing we've done lately, I think the suspicion is the monitoring infrastructure adds a pretty significant overhead on throughput. So I think potentially turning off the central monitoring and just running with distributed, putting it nicely, monitoring probably will give you a factor of 10 increase in throughput, which is probably in line based on your job size is sufficient to keep a decent Perlmutter allocation busy. Now, I don't know what Bjorn would say about Perlmutter being a CPU system, 128 cores.
We would be happy if more GPU were
Oh,
used.
surprise.
But even had his job, that would be fun.
I could hear Bjorn behind me freaking out.
All right. I kind of rushed through this a bit, but I guess what I was thinking is these job production managers could run just one per node, and so that maybe handles some of these issues of how we have to build and submit jobs. Makes it easier to make the executor performant.
Yeah, I mean, it'll make the executor performant. You'll end up with the same distributed, decentralized monitoring. So just turning off monitoring might get you similar performance with the same output at the end, but you still don't have great integrated monitoring. Anyway, I think those are great points, David. All 6 or 7 of them, I think it would be great to actually work through all of them with you and others.
Agreed. All right, thank you, David. Lee Liming now.